Volcanoes act out in every possible way. Like a moody person, they can erupt in violence, or steam silently, lazily creep along, or self-destruct. A volcano's origin determines its temperament. Many volcanoes erupt along subduction zones. Here, the great tectonic plates of our planet's surface push against one another. Along this margin, where one plate is rolled beneath another, we find the most violent volcanoes. Explosive eruptions fit our image of a volcano. They create large cone-shaped mountains. These erupt when magma below forces its escape. Fueled by expanding gases and boiled groundwater, the excess heat blasts through. Volcanoes like this often have alternating layers of different volcanic materials: ash, cinders, and lava. These layered cones are called composite volcanoes. Hawaii isn't near the joining of two plates, but it's a hotspot of volcanic activity. What fuels it? The Hawaiian Islands are hotspot islands, created when a pool of magma breaks through a thin spot in the crust. As it burns through, the plate moves along 4 inches a year. One island is carried away to cool, while the next one is created, assembly line fashion. On the Big Island of Hawaii, Kilauea has been erupting since 1983 and shows no signs of letting up. It's an example of a second kind of volcano, the shield volcano. The central crater is called a caldera. It still steams, but probably won't erupt violently. Farther out, lava oozes and flows, creating new real estate as it cools. The wide flow is what creates a shield volcano rather than a cone. This new unstable bench is pure basalt. Sometimes the flows are only inches from the surface. The thick, honey-like lava, typical of Hawaii, cools into a harsh, barren environment that can take years to support life. Cinder cones are a third kind of volcano. Mexico's Paracutin is a dramatic example. Like composite volcanoes, they can be explosively violent visitors to the surface of our planet. They burst forth with enormous quantities of ash, cinders, and lava fragments. They rapidly build volcanic mountains, but never as wide as shield volcanoes, or as high as composites. Cinder cone shape is determined by the size of the ejected material.
18,000 years ago, massive glaciers locked 1/3 of the land on Earth in their icy grip. These rivers of ice gouged their way through mountains, smashed boulders to bits, and scoured areas of the Earth flat. Then temperatures began to rise. The glaciers began to retreat, exposing a changed landscape. Glaciers helped form the lakes and rich soil of the Midwest, the fjords and peaks of Patagonia, and Yosemite Valley in California. Here, the glacier bulldozed its way through the mountains, carved out a U-shaped valley, and left behind sheer cliffs like Half Dome. A glacier begins when snow begins to fall faster than it melts. As the snow accumulates weight, it compresses. The light, fluffy crystals turn into firn, a dense, grainy ice. As years go by, the weight of accumulated snow on top increases. The ice begins to move under its own weight. No speeding tickets here. The glacier moves under 1 inch per day. The bottom layer, slowed by the ground, moves less than the top. The strain cracks the ice, creating giant crevasses. Warming at the end of the last ice age reduced the Earth's glaciers, but it didn't get rid of them. Today, more than 1/10 of the land is still covered in ice, and that ice holds a wealth of information. Scientist Keith Eckelmeyer measures Columbia Glacier in Alaska yearly in order to get a jump on global climate trends. Columbia has retreated 8 miles from its terminal moraine, the pile of rubble left at the end of the glacier. As it shrinks, it calves huge icebergs off into the sea. No one knows for sure whether this is from global warming or just part of the natural cycle of temperature and ice. By studying air trapped in the ice, researchers reveal the history of Earth's climate and look past the current warmth for clues to the next ice age.
These giant gashes in the Earth are reminders of our planet's awesome power. They are fault lines, fractures in the Earth's crust where huge slabs of rock slowly grind past each other. Most faults we can't see, but here in California, the San Andreas Fault is visible at the surface.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with one foot on one tectonic plate and one on another. In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
The San Andreas Fault sits on the boundary between the North American and Pacific plates. It's called a strike-slip fault, a place where two plates collide and try to slip past each other. As these plates move or creep in different directions, sometimes they get stuck. The longer they stay stuck, the more tension builds and the bigger the eventual quake. In other places, the plates move smoothly past each other. These areas buckle as the Earth shifts. The changes are subtle. Roger Billam keeps track of these changes with his creep meter, a device that measures movement along the fault. A computer collects data every minute for a year. This jump in the graph tells him the Earth shifted about 5 millimeters in a couple of hours. A small shift like this can have huge consequences for us.
That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field, there aren't any people, but further north, this creep process and the things that are happening beneath the Earth are far more sinister.
The San Andreas Fault and its branches trigger more than 10,000 quakes a year. Sometimes the results are devastating. Just ask the people of Los Angeles or San Francisco. Over the last 2 decades, major quakes rocked both of these cities. Life goes on, but the risk remains. In an area this active, the next violent tremor could happen at any time.
The Earth's forests are disappearing. People are cutting them down faster than they can regrow. These forests sustain millions of species, including people. They provide wood, foods, medicines, fuels such as charcoal, and countless other products. They bind the soil and temper the climate. Evergreen forests and seasonal forests, rainforests and dry forests, low forests and high forests, all are valuable beyond measure. The oceans are vital to life on Earth. Nearly every part of the marine environment is now polluted, even the polar seas. Contamination destroys estuaries and coral reefs, the nurseries of marine life. Fish are harvested faster than their populations can be naturally replenished. Each day, the methods of modern fishing take a heavy toll on our marine resources. Mountains are the supreme expression of the landscape. They define physical space by making natural barriers and cause far-reaching effects on the weather. Mountains provide unique habitats and shelter for wildlife and humans, but also pose many dangers. Mountains are a source of inspiration to many cultures. Certain peaks are even regarded as spiritual centers. A number of great plates compose the fractured surface of the Earth. Slowly oozing molten rock far below moves the plates over, under, against, and past each other. As a result, the ocean basins grow wider, continents float to new positions, chains of mountains are thrust up, faults and chasms rend the landscape, and volcanoes spew fiery material from the depths of the planet. The seas are constantly in motion, stirred by winds, the spinning of the Earth, and the gravitational pull of the Moon. Tides depend on the Moon's position, on ocean currents, and the configuration of coastlines. Tidal flows may raise sea level by several meters. Waves are an expression of energy. Their intensity ranges from mild to awesomely powerful. Every year, some 100 of the world's 500 active volcanoes erupt. They spew ash and debris and spill lava in enormous quantities, transforming the surrounding landscape. A single blast can alter a mountain's profile and obliterate nearby life. But even as they wreak destruction, volcanoes create new land and enrich the soil with a rain of fertilizing ash. The world's wetlands are in danger. People ditch them, drain them, dike them, dump waste in them, and drown them behind dams. Swamps, bogs, and marshes are lost to create land to farm or build upon. As a consequence, the world is losing its natural water filters, its buffers against floods and erosion, and the critical habitats and nurseries for a myriad of species.
Earthquakes like the one that struck Kobe, Japan on January 17, 1995 are massively destructive. These earthquakes are caused by huge pieces of the Earth's crust, called tectonic plates, either sliding against each other or pushing into one another. While the science of predicting earthquakes has not yet been perfected, new structures are designed to minimize damage and casualties.
The fourth major hurricane of the season slams at Jacksonville Beach and points north and south along the Florida-Georgia coastline. Winds of 100 miles an hour and upwards.
People have long known the destructive nature of hurricanes. These storms, bringing heavy winds and rain, may last several hours and have a diameter of over 480 kilometers or 300 miles. Hurricanes form over warm tropical oceans in areas of low air pressure. They consist of high-velocity winds blowing in a circular motion around a low-pressure center known as the eye of the storm. The only defense against hurricanes is through early warning and preparation. Meteorologists can now track these storms and measure their force through the use of radar and satellites.
It looks like now the center will pass inland sometime near dawn. Well, as it goes across the Florida Peninsula, of course, we're going to have significant damage here in Miami, Fort Lauderdale.
The National Hurricane Center's prediction was correct. In August 1992, Hurricane Andrew caused billions of dollars in damage and killed a number of people when it hit the southeastern United States.
Thunderstorms form when hot, humid air rises rapidly in the atmosphere, causing rain, lightning, and thunder.
After lying dormant for centuries, the Soufriere Hills volcano on Montserrat rumbled back to life in 1995, forcing an evacuation of the southern portion of the island. A major eruption destroyed the capital, Plymouth, in August 1997. Superheated gas, rock, and ash cascaded down the mountain, setting the city on fire. Further eruptions covered the charred remains in ash. In the morning hours of September 19, 1985, the worst earthquake in Mexico's history devastated the nation's capital. Many of Mexico City's buildings crumbled as 3 minutes of intense tremors rocked the area. Thousands were buried in the rubble. Efforts to help the victims were hindered by extensive damage to the city's hospitals.
There is a tornado on the ground near the Sykes Center area in Wichita Falls. Please take cover. EPO. Where's EPO? Okay, that thing looks like it's moving directly east. It's on the north side, still on the ground. Why don't you buddy go ahead? Golly, I'll tell you what, they've got a bad one up there. How wide is it? 35, let's say about 10 city blocks wide. That's a big one, Vic.
On April 18, 1906, the city of San Francisco, California was rocked by an earthquake estimated at 7.7 to 7.9 on the Richter scale. The earthquake started a fire that lasted for 3 days, destroying much of the city's downtown. Thousands of people were left homeless. Many buildings left standing were so damaged that they had to be torn down. In the wake of the disaster, refugee camps sprang up throughout San Francisco. Families who had lost most or all of their possessions were forced to live in tents in often squalid conditions. Looting was a serious problem, and food was carefully rationed. Overall, the Great San Francisco earthquake and its aftermath destroyed over 28,000 buildings and claimed over 3,000 lives.
On December 4, 1991, violent explosions from Etna's southwest crater filled the air with volcanic rocks and fountains of lava. The phenomenon, which lasted 473 days, produced around 235 million cubic meters of volcanic material, creating eruptive vents 2,200 meters above sea level in the area of the Valle del Bove. The lava face, divided into two branches, traveled some 9 kilometers at its greatest extent, stopping 740 meters above sea level. Its movement profoundly altered the morphology of the area it covered.
Energy in the form of heat from the sun is the engine that powers our weather. Heat not only gives us warm weather, it also leads to tornadoes, hurricanes, blizzards, and rain. Sounds impossible? Just think about the sun. It pours out electromagnetic energy in all directions all the time. It radiates heat waves that travel through space and reach the surface of the Earth. Energy from the sun gets absorbed by the Earth and converted to heat. Since our Earth is tilted, sunlight strikes it unevenly. At any given time, some places on Earth are heated more strongly than others. This uneven heating helps drive our weather. As the surface of the Earth heats up, it heats the air above it. Like these bubbles, warmer air becomes thinner and lighter, so it rises. And as it does, cooler air moves in to take its place. This movement of heat through the fluid of air is known as convection. It creates areas of high pressure and low pressure and gives us our winds. Even tornadoes. We can think of our atmosphere as an endlessly moving river of air, full of currents, eddies, and winds. Together with water, it helps distribute heat around the planet. Water both retains and releases the heat energy from the sun. So it too plays a key role in our weather. The oceans efficiently store heat and carry both warm and cold water around the globe. The differences in heat between the land and sea greatly influence local weather. To get a better idea of how water carries heat, just look at a puddle. When the sun heats the puddle, the water evaporates, carrying heat energy with it. Water becomes invisible vapor that adds moisture to the air. This water vapor rises until it cools and condenses into clouds that bring snow and rain. Stored heat energy is released in the process, which sometimes powers a thunderstorm. The energy released when water vapor turns into a thunderstorm is mind-boggling. It could power New York City for 2 months if only we could harness it. There's that old saying, if you don't like the weather, wait a minute, it'll change. Thanks to the heat of the sun, this is definitely the case. We live on a planet whose crust is miles thick with rock. Rock is the basic unit that makes up our solid Earth. It supports everything, from the ground we walk on to our oceans, our deserts and mountains. When we talk about rocks, we're also talking about minerals. All rocks are made from more than one mineral. Geologists define a mineral as a naturally occurring solid that has a distinct chemical composition and consistent internal structure. Minerals can be elements or compounds. Gold, silver, and diamonds are 3 examples. The Earth is constantly changing, and so are the rocks and minerals it contains. They get redistributed and recycled over and over again in a process called the rock cycle. Over millions of years, rocks are continually made, changed, and destroyed. At the surface, people break down the Earth's rocks and put them to good use. Throughout history, we've learned to depend on them. Today, they help cover our roads, support our buildings, and decorate our lives. Forces of nature also take their toll on rocks at the Earth's surface. Wind, water, and gravity are always at work to wear down or erode the rocks around us. The results can be very dramatic. But for all of this destruction, new rocks are constantly forming. Some particles of rock get deposited and hardened into sedimentary rock. Others get buried, compacted, heated and recrystallized beneath the Earth's surface. Temperatures are so hot at great depths in the Earth that rocks and minerals often melt and become liquid. Over time, the liquid cools, creating new rocks that eventually get pushed to the surface again. Sometimes this process happens quickly during events like volcanic eruptions and earthquakes. But most of the time, it takes millions of years. As a result of this ongoing cycle, the Earth holds a tremendous variety of rocks that differ in the minerals they contain. They vary in color, texture, permeability, and so on. Geologists study these rocks in search of valuable clues about the history of the Earth. Like rings in a tree, they hold information about past environments and the events that formed them.
From the soil under our feet to the stars above, matter makes up everything in the universe. Matter comes in 4 states: solids, liquids, gas, or plasma. In solids, molecules are tightly packed and maintain their shape. Add energy, like heat, and the molecules begin to separate and melt into a shapeless liquid. More energy, and matter turns into gas. Superheated gas becomes plasma, the 4th state of matter, where electrons tear away from their atomic nucleus and float freely around it. Even in cold climates, solids like this snow turn to water when heat energy pushes the temperature above water's melting point. Liquids can't hold solid shapes, but they do have volume and move to fill the space available, even space as big as oceans. While it's obvious that ice melts, even rock solids melt when they're subjected to enough energy. Rocks melted by the heat and pressure deep in the earth erupt from volcanoes as liquid magma and lava. Gas molecules are farther apart and have even more energy than liquids. Gases, like air and hydrogen gas in the universe, have no fixed shape or volume. Superheated gases in the universe are plasma. Plasma makes up more than 99% of our visible universe. Its electrically charged particles are the stuff of stars. Physicist Albert Einstein came up with an equation, E equals mc squared, to help explain the relationship between energy and mass. The simplest interpretation suggests that matter can be converted into energy and energy into matter. The theory helps explain the curious beginning of the universe when an enormous amount of energy became matter.
All right, we're on target, Phil.
No matter what state matter's in, it demonstrates the property of inertia. This natural law means that matter doesn't change unless it's made to by some outside force. Ice may be moved to melt, and an avalanche to slow, only when moving forces, such as heat, act on them. The light of our lives comes from the sun and other stars. A form of electric and magnetic energy, photons of light travel through space behaving both like particles and waves. Like ripples in a quiet pool of water, changing electric and magnetic fields of light can be seen far away from their point of origin. Light travels at a constant speed for hundreds, thousands, even millions of years to get here. There's distant light in the universe, billions of years old. Even the light from the star nearest our sun, Proxima Centauri, takes 4.3 years to arrive, and that's traveling at 186,000 miles per second, the fastest speed in the universe. To collect light, our eyes function something like cameras, with lenses and pupils controlling the amount of light absorbed. Much of the light in space is too distant for our eyes to see detail and color without assistance. To peer farther into space, Galileo pioneered the use of a telescope in 1609. Like all lenses, these refractor telescopes bent parallel rays of light passing through glass and converged them on a single focal point. Images were magnified with an eyepiece. These early telescopes collected no more light than modern binoculars. To see farther, these telescopes would need to become larger, but they could only grow so much. Lenses wider than 3 feet may distort, causing a distortion in the image as well. Refracting telescopes gave way to reflectors. They bounce light from one or more reflective surfaces to a prime focus. Reflective mirrors need less support than lenses and can be made larger than refracting telescopes. The mirror on this reflector is nearly 14 feet across. The reflector has 2 mirrors. Light bounces off the big mirror, then off a small mirror to a focal point where it's recorded and stored electronically. Today, the largest reflector telescopes are in Hawaii, on a 14,000-foot peak called Mauna Kea. The Keck telescope's 2 mirrors are more than 30 feet across and are made in movable pieces that can shift to compensate for changes in the atmosphere. As better and better telescopes help us capture light farther and farther away, we can see light older than man and as old as the universe.
The polar ice sheets of the Arctic and Antarctica cover 1/7 of the Earth's surface. Because they cap the ends of the Earth, the poles each experience 6 months of near constant daylight and 6 of the darkest winters on the globe. Home of the South Pole, Antarctica is a continent of extremes. The highest, driest, and windiest place on Earth, Antarctica is technically a desert, trapping 70% of the world's fresh water in 90% of the world's ice. There isn't even enough water in the dry air to make snowflakes here. Instead, Antarctica produces diamond dust, best seen at night. A polar meteorologist catches a little dust and unveils its flat, hexagonal shape under a microscope. During the day, diamond dust creates an eerie halo in the sun. Over millions of years, the dust has collected to create an ice cap 3 miles thick. But at the opposite end of the globe, the North Pole boasts the largest expanse of sea ice. An ocean of ice covers 5.5 million square miles. Shipping lanes choked with ice make dangerous highways, and ships with bows made of 12-inch steel must crack and cut their way through. Miscalculations spell disaster. Ships running the lanes early or late in the 6-month season are often supported by helicopters, charting the safest routes from the skies. South of the North Pole, Greenland glaciers push to the sea and carve as many as 15,000 icebergs in a year. The rogue chunks of ice may tower as high as office buildings, but even greater expanses float unseen below the water's surface. To protect ships from running into icebergs, the U.S. Coast Guard flies an ice patrol. They relay warnings to ships on a collision course.
Roger, got an unidentified target 6 miles off 3 o'clock on the aircraft. Can't see it through the under.
While polar ice poses problems for man and machine, the loss of it may prove more devastating. For the last 30 years, the ice shelves around Antarctica have been shrinking. They're disappearing at a rate of more than 1% every 10 years. Global warming, caused by a buildup of man-made greenhouse gases, makes a little more ice melt each year. Melt all the ice sheets, and the sea level would rise a devastating 200 feet. Remote as they are, the ice cap's influence travels the globe.